Good afternoon and welcome. We have a guest speaker today whose name is Professor Yuji Nakamura, and he is from Hokkaido University in Japan. He's currently on a sabbatical for 10 months in UC San Diego, and he has graciously accepted an invitation to come to WPI and give us a talk on electrical cable fires, which is the research he's doing currently while at UC San Diego. With that, welcome Professor Nakamura. Yes.
Thank you very much. Good afternoon, gentlemen. My name is Yuji Nakamura from Hokkaido University. Right now, I'm in a sabbatical leave at the UCSD. That's contracted 10 months. I already spent the half, so the rest of the half I've tried to enjoy the San Diego. First of all, thank you very much for Professor Ali to give me a chance to coming here to share with you about the recent research on the cable fires. This research is actually firstly motivated by fire in the space. Since I'm in the mechanical and space engineering department, so this is kind of one of the obligations for us to involving for space issues. So this is the kind of one of the space fire research. That's my original topics. Anyway, let me start with the talk. And this is the contents. Mostly I'm talking about the small scale stuff, but let me start with my introduction and some motivation, and it goes to a small scale test and upper scale test, and it goes to summaries. You have to know who I am, and my name is Yuji Nakamura, as mentioned before, and this is my CV. I spent the 1 year at the University of Kentucky 14 years back. Then I got a academic position in Japanese university, Nagoya University, as a research associate. This is kind of like a postdoc, non-tenure. Then after I received my PhD, I got a chance to come to NIST, building fire research laboratory, as work for researchers to involving the project of the microgravity flame spreading things. Then after that, I got an assistant professor, then promoted to the associate professor at the Hokkaido University. This is the current my position. Right now, I'm in the business scholar at the UCSD. Where is the Sapporo? Where is I'm coming from? Is that over here? Japan has 4 islands. This is the main island, and this is the very north part of the island. The latitude is 43 north, so this is almost same as Worcester. So you can imagine that how cold it would be. The land is about this much, and the population of Sapporo is almost 2 million people. So it's quite a large city. The average temperature is 8.9 degrees Celsius. And this is the highest, maximum. This is the lowest in the history. And 7.6 days is, you can guess that this is the day we had above 30 degrees Celsius in the summertime. So only 7 days we have very hot summer. So we have to take a vacation for 7 days to avoid these kind of things. Our university actually encourages us to take off in the summertime. 265 days is the average for we had either snow or rain. So we had a lot of snow and rains. 360 centimeter is the total snow height we have annually. This is the average. So this is quite much. So it is a couple of the pictures in Sapporo city, and this is always we have in the snow time, and we don't know what is my car. It's always covering the snow, but the airplanes goes quite well. I mean, they flew most of the day without any kind of problem. So airport can be treated quite well. And this is the kind of scene I always fight with in very early morning. We have to make road. Otherwise, we don't go to the university. What the great thing is in Sapporo is, of course, the Sapporo beer. This is one of the most important, famous things in Sapporo. But we can enjoy the winter time by like that. This is the winter festival in Sapporo. This is actually made by ice. It's very big architecture that we're celebrating in the icy weather. Of course, we can enjoy the hot tub, and there are many wild animals. You can enjoy that. So a lot of natures, then a lot of the hot part and a very cold part. Very nice to stay at Sapporo. Our university is located near the Sapporo station, so it's very easy to come to the university. So if you have any chance, I welcome you to come. The size of our campus is 1 mile square. So I don't know this is really large or not, but this is the largest in the Japanese university. The faculty student members is total, our student is 80,000, and my faculty is 3,800. In terms of engineering, a student is about 4,000, and a faculty member is about 300. Now, we had a good connection with the state of Massachusetts. This guy named William Clark. He was the vice president when we founded our university. He was invited from Massachusetts Agricultural College. So boys be ambitious. This is the word he actually remained to the Hokkaido University. So we have to be ambitious. And we had a good English education program right now. So you don't need to speak Japanese in our university. If you come to involve this program, you can just do it in English. So if you're interested, just hit this page, then you can get information. You don't need to pay anything. So the probably university will pay for it, or government will pay for that. So, but you have to pass some qualification test, but you have a lot of chance to come to Japan. And also we have an international student center as well, so we can take care of the international student as well. So this is the public relation of my university, but I'm going to research part right now. Let me start with the original motivation. As mentioned before, I'm coming from mechanical space engineering department. So everything has to be related on the space or aerospace engineering. The cable wire, the wire combustion or cable combustion, why I'm doing this is that one of the important topics, fire in space. But doing fire in space is usually doing the microgravity things. But I'm trying to get low pressure conditions. This is my original idea. Since there's many low pressure conditions in the aerospace engineering, but not so common on the Earth, but going to fly, aircraft cabin, of course, reduced pressure, almost 80 kilopascals, and space suit, it's almost 30 kilopascal, so it's one third of the normal pressure. So in aerospace engineering, the low pressure environment is quite common. So this is one of the motivation. I'm starting with the low pressure wire cable combustion. Why we selecting low pressure conditions for aerospace engineering is very easy to understand, because outer field is highly vacuumed. So if the inner, for example, this is the aircraft cabin, then you have pressure differences. If you keep here as normal atmospheric pressure, you have a lot of pressure differences from inside to outside. So to fight with this kind of pressure difference, you have to be very rigid. This structure has very solid, which means that you have to be much more materials, and you have to structure quite well. But if you're reducing the inner pressure, you can reduce the delta P which means that you can simplify the structure or either you can simplify the noise. So this is the reason why you're applying for low pressure conditions in aerospace engineering. But if your human has to be here, so this is the kind of a limited condition. So we need a certain amount of pressure, partial pressure of the oxygen. Otherwise, we can't live. So the partial pressure oxygen has to be around 21%, right? 21 kilopascal or something like that. But if you reducing the total pressure but keeping the some amount of the partial pressure of the oxygen, the result is oxygen concentration has to be higher. So this is one of the reasons why the aerospace engineering need to considering about the fire. One good example, I don't say a good example, one tragedy example is Apollo 1st. There, in the inside of this cabin is actually 100% of oxygen. That was the first trial for the NASA's. That was the first choice for the NASA's. But unfortunately, they got some electric circuit fault. Then try to catch the fire. Since this is the flow of the oxygen, it can burn very, very well. Apollo 1st, you have actually 100% oxygen, and total pressure inside the cabin is 20 kilopascals, which is the partial pressure oxygen is the same as air, same as the ground, but you have the full amount of oxygen over here. But that's easy to be captured, easy to catch the fire. However, since that time, the effect of the oxygen on the fire research is, of course, extensively studied. However, pure effect of the lower pressure condition has not yet understood. How about the aircraft? This is the statistics of the aircraft crash or aircraft fire accident in Japan, not in the world. But you can see that every year we have at least one fire happens in the aircraft. This is the one of the. This is not the Japanese one, but this is the the famous one. Swiss Air 111 was the 1998. They got the fire near the cockpit, then they burned everything. They didn't get the tragedies. As mentioned before, aircraft cabin is low pressure conditions, so low pressure electric fire should be understood quite well in aerospace engineering applications. So this is the first motivation. Try to capture what is the pressure effect, lower pressure effect on electric fire. That is my first intention. And try to understand what is the pure pressure effect, low level of pressure on the fire characters. Not the high pressure, but the low pressure. This is the reason I started with a small-scale test of the cable fire, especially to looking for low-pressure conditions. Now, what actually we are trying to burn is cable like this. As you know, that cable has inner conductor with outer sheath. Outer sheath, you have insulator. This conductor has to be metal. Otherwise, you can't transfer the electrons. And the insulator using over here mostly is polyethylene. Why? Is that the polyethylene is very, very good performance for the insulation. And also, this is very light and very cheap. So conventionally, polyethylene is quite heavily used for the cables. So again, inside, you have metal. Polyethylene was coated outer sheath. So this is the simple specification of the cables. So if you try to burn the cables, inner core doesn't burn. The burning material is outside of the polyethylene. That's the kind of like a basic. So now you can understand what is the feature of the cable combustion as compared to the normal solid combustion. The upper figure is showing that the a schematic view of the frame spreading of some polymer, thin polymer, for example. You have flame, you're progressing of this way. Usually frame spreading rate, if you're thinking about a thin polymer case, you have a constant frame spreading rate you can observe. And this frame spreading rate has to be controlled by heat transfer from the frame to the unburned solid. If you had a large heat flux, you get the higher frame spreading rate. That's quite obvious. However, if you're thinking about the thin polymer case, the conduction through the solid phase is quite limited, almost negligible. However, in the cable case, as mentioned before, we have we have metal here, so we get a lot of heat can be transferred through the metal wires. So there is actually two routes for the heat can be transferred into the unburned zone, which is the same as the upper figures. We have direct heat transfer from the frame to the unburned solid. The second one is heat through the wire to preheating up the unburned solid. So these two routes, thermal route, has to be considered. That's the one of the good feature, the important feature for cable combustion. So this is remembering. This is very important. But to understand, since this is very important, you have to know how much these are important. However, if you buy the cables, each cable has slightly different. I mean, if you buy these things and try to burn, then again, next day you buy these things, try to burn, probably you get the different results because you have the different slightly fluctuation for the materials. So we want to fix the materials just for the purpose of the combustion, combustion researches. So we made simulated the cables by ourselves. Of course, I don't make. I ordered to the cable companies to make those kind of cables for us. This is well controlled, which means that we know what is the thermal conductivity of the metal wires inside, and also how much thickness of the polyethylene. We put actually very pure polyethylene coated. So we know the material to be burned. We know the material to be heat transferred. So this is the good way to do the research matches. There's a variety of the cables we actually made. Inner core metals has to be nickel chrome or iron or copper, these three types. Why these three types we selected is we have the different, quite much different thermal conductivities. And the thickness of the pure polyethylene is also fixed at almost 0.15 or 0.2 millimeter of the thickness. This is really uniform. These companies made a very good products actually for us. So really a solid material we can get. So reproducibility is really high. But now on, let me talk about the results of the base case, nickel chrome 0.8, which means that the inner core is made by nickel chrome. The outer diameter of the nickel chrome is 0.5 millimeter thickness diameter. The thickness of the polymer coating is 0.15 millimeter. It's very, very thin. This is the base case. Let me talk about the results of this base case. The spreading test is actually followed by JIS 3005. This is the standard test in the Japanese company, Japanese standard organization setting this kind of test. We taken this horizontal test. Sample pressed by horizontally, then you heating up, then get the frame spread. This is the apparatus. This is very simple. You have enclosure, the combustion chamber. You just get the sample holders, put the wire in, make an igniter over here, make the frame. The one side of ignite, the one end you ignite, you're generating a frame, then that frame is propagating to the other side. Just one-way propagation we're observing from the outside. Since I'm looking for the low pressure conditions, this chamber has to be controlled by the pressure. The sample is polyethylene coated nickel chrome wire, as mentioned before. Again, specification of this wire is 0.5 millimeter of the diameter. Thickness of polyethylene is 0.15 millimeter. It's very thin. The total pressure inside the chamber is controlled by 20 kilopascal to the 100, which is, this is 1 to the 5th of the normal pressure conditions. 100 kilopascal is almost similar to the standard pressure conditions anyway. So this is a subatmospheric range. The gas composition is actually fixed because I'm trying to looking for the pure pressure effect. I don't want to thinking about any kind of the oxygen effect. So oxygen percentage is fixed, the same as air. Oxygen is 21% diluted by the nitrogen. Okay, we do not consider high oxygen field at this moment. We did actually, but I don't talk at this moment. Okay, we fixed the oxygen percentage, but we're reducing the total pressure, which means that if we go into the low pressure condition, the partial pressure inside the chamber is actually reducing. I checked this one, maybe, okay, it doesn't work. Actually, I get the movie here, but sorry, it didn't work. Once igniter was set over here, once the igniter is on, frame generated, and then frame is propagating from this way to this way. It's quite simple. We're tracking the frame front as function of the time. This is the 100 kilopascal, which is normal pressure conditions results. That's really, linear correlation you can find, which means that you have constant frame spreading rate you can achieve. If you go down to the low pressure to 40 kilopascals, frame front behavior is slightly showing the zigzag motion, but average you can fit like that. So you can define average frame spreading rate in low pressure conditions. This is the direct picture of the low pressure combustion wire spreading case. This is normal pressure case, and you go down the pressure to the 1/3. If you go down the pressure, obviously frame height getting reduced, frame width getting increased. So it almost approaches to the non-buoyancy flow case. But actually we have the buoyancy flow. But since in lower pressure conditions, diffusion transport is almost dominant, so you have almost spherical frame like that. This is the backlight images, so you can see that the flame, you can slightly see that, but you can more clearly see that the polymer actually melted over here. Polyethylene first melt, then going to evaporate and then decompose to make the gas phase. The gas phase, gasified polyethylene was reacted with the ambient oxygen to form the flame like this. So melting part is quite obvious. Always melting part will be associated with the frame spreading phenomena. Since we can define the frame spreading rate, how that respond by the pressure, this is the results. If you go down the pressure, again, we fix the pressure concentration, the oxygen concentration in the chamber, always 20% of oxygen. So if you go down the total pressure, which means that your partial pressure of the oxygen inside of the chamber is also reducing. So which means that the molecular number of the oxygen is reducing. But even though molecular number of the oxygen is reducing, you have higher frame spreading rate in lower pressure case. That sounds like a strange. First, I thought this is kind of like a strange, but actually it does. And if we make an obstacle like this to confine the flow or confine the volume, then we have the different trend like that, something like a leveling off. But if you pretty much open case, but of course you have the enclosed chamber like this, very, very large chamber like that, and you get this kind of trend. I don't say almost linearly, but as you're reducing the pressure, always frame spreading rate is increasing. Then approach to the extinction condition, it's going to die. So this is the pure pressure effect. If you're reducing the pressure, always frame spreading rate getting higher. To understand why, we try to get more information about the spreading processes. This is one of the results for temperature profile prior to the flame in the preheating zone. Flame over here, flame is moving this way. We split slightly of the polyethylene coating of the samples. Then I ask my student to welding the thermocouples onto the wire. This is the perfect picture actually, but my student spending 1 hour to get this picture. Then to get these results, they spent two days. Actually, to welding the very, very thin thermocouples onto the wire is very tough work. I really appreciate my student for dedication work. What we got is that the closed case is 100 kilopascal, which is normal pressure. The reducing pressure is the open case. So let's look at the blue one. If you have the normal pressure conditions, temperature profile prior to the flame is like this. However, if you go down to the pressure to 40 kilopascals, obviously more longer portion will be heating up. So preheating region is longer. So this is quite reasonable why you get the higher frame spreading rate. So this is one of the good reason for it. Then I try to estimate what is the thermal balances actually happening over there during the frame spreading case. We assuming the frame is almost spherical, and we know the frame temperature we separately measured in low pressure case. Then if you go down to the 30 kilopascals, very, very low pressure case, you have almost spherical frame. So probably this kind of assumption may be quite right in lower pressure case anyway. So we know the temperature, then we assume the shape. Then we can calculate, very roughly calculate how much heat will be transferred directly from frame to the samples by conduction. Then Q3, how much heat will be transferred to the head, that can be calculated by this measured results. So this heat flux will be calculated by the measured one. And eventually, how much the total heat will be received for this polyethylene is back to be calculated by frame spreading rate, because we know the frame spreading rate, which means that how much volume will be consumed in a certain time. We know that. That's why we know this Q, the number of the Q, which is Q1 plus Q2 minus Q3. We know this number. We know the number. We can calculate the Q1. We can calculate the Q3, which means that we can calculate the Q2. So Q1, Q2, Q3, we all know that, and we're summarizing over here. 100 kilopascal case, total heat will be gained is like this. The 50 kilopascal case is like that. The Q1 directly from frame to the solid is actually higher in low pressure conditions. If you're looking more a comparison with Q1 and Q2, always Q1 and Q2 has almost the same level, but of course Q2 is more large. It's larger than Q1, almost 2 or 3 factor of the 2 or 3. But the important thing is Q1 and Q2 is almost the same order of the magnitude. So which means that these two are both important to determine the frame spreading rate. So only Q2 doesn't work, only Q1 probably doesn't work. So Q1, Q2, these two heat transfer process is very important, which is we expected, but we can confirm by this figure. Again, in terms of the effect of the pressure, if you go down the pressure, what actually we found that the frame will be decreased and the frame width is enlarged. So you can draw like that, normal pressure case like this, lower pressure case like that. So which means that lower pressure case, you have more fuel was covered by the flame. So simply this is the reason why you have larger Q1 and why you have more heating up to the front. So this is the reason why low pressure case has more faster faster spreading rate as compared to the normal pressure case. So if this geometry reason is the main reason, we can understand that what is the microgravity conditions will be happening. Again, wider flame could increase Q1, that increasing the frame spreading rate. If you go down to the if you down to the pressure, you almost seems like a spherical frame like this. Also, you go down to the gravity, you also seem like a spherical frame like this. This is actually in the microgravity wire combustion case. Even though the color is different because this has an imposing flow, so you have a lot of soot over here, but the frame shape is quite similar. You have elongated. By this picture, of course, you can see the similarity between the low pressure flame and the microgravity frame. Of course, this can be theoretically done by considering the transport pi numbers. For example, Reynolds number or the Grashof number like this. Reynolds number is scaled by pressure first. The L is length scale first. The Grashof number is pressure second, and the cubic of the length scale multiplied the gravity term. So if you are dealing with a small scale stuff, which means the L, liquid representative length scale is smaller, your Reynolds number or Grashof number can be smaller. And also, if you go down the pressure, your more smaller Reynolds number or a more smaller Grashof number will be expected. What is the similarity between the microgravity and the low pressure case can be understood by this Grashof number correlations. If you down to the pressure to the half, which means the same Grashof number can be done by quarter of the gravity. So if you go down the pressure, which means that you have the lower gravity case. That's the Grashof number similarity is really revealing that. So we're dealing with the low pressure case, we can simulating for microgravity case. Since microgravity combustion, wire combustion, we actually did this experiment, but this is really costly. You need to go to the some expensive stuff to creating a microgravity facilities to use the microgravity facility. But a low pressure case is very, very easy, very cheap. You can do it in your laboratory. So if you can simulate in the microgravity case, it's much easier. So this is one of the good example reducing the pressure. The same reason probably you can achieve that if you go to the low pressure case, as mentioned before, frame spreading rate is increased because you have wider flame. So how about the microgravity frame? Microgravity, you also have the wider flame. Then believe it or not, microgravity case, as compared to the normal gravity case, frame spreading rate is higher. So almost similar, higher than actually we can get in a low pressure case. So which means that the reason why microgravity gets the faster frame spreading rate has to be the same as why you have faster frame spreading rate in lower pressure case. So exactly you can have longer or wider frame like that. So geometrically, probably the one of the important reason to determine frame spreading rate behavior. Until now, we just stick with one cable, one testing cable like this. But we have the variety of the cables, so try to find out what is the load of the effect of the conductor, which is material, nickel chrome, iron, copper material. We change that, and we change also the relative size of the diameters of the wires, and see what happens. This is a direct picture. You will see that in different frame images, but always you can see that in lower pressure case you have shorter frame, but you have wider frame. That's because of that, in any core material we used, always low pressure case give you faster frame spreading rate. However, it's quite obvious copper case is much faster frame spreading rate can be achieved just because copper has a more highly conducting material like this. Thermal conductivity is most maximum in the copper case, in the middle of the iron, and the most minimum for nickel chrome. So this is quite reasonable. If you have the more heat transferred, you have higher frame spreading rate. This is quite reasonable. How about the core diameter effect? If you change the core diameter like this, small diameter to the large diameter, frame spreading rate is getting decreasing. This is not limiting for the nickel chrome case. Same things happening for the copper case. If you have the larger core diameter, you have slower frame spreading rate, which means that core acts as heat sink. As mentioned before, core is the heat conductor, of course. So that can promoting the faster frame spreading rate. But the core has to be heated up itself. So if you have a lot of the core, you need more heat should be absorbed to increase the temperature up to the melting temperature of the polyethylene. So that can be thinking about the heat sink. So if you have the larger core diameter, you have larger heat sink too. So you have longer time to be heated up. So that's reducing frame spreading rate. So the wire is not only the promotion of the frame spreading case, but also you're actually prohibiting sometimes. So arranging for how to design of the wire, then you can actually design for how much frame spreading rate you can achieve, or how to reducing the fire risk or fire damage of the wires. This is the another interesting issues. This is the close-up view of the burning polyethylene wires over here. As mentioned, we have molten polyethylene over here. If you see the movie, sorry, I could have put the movie over here. This you see the bubble formation over here. Then you have some kind of rotation motion over here. So there's a lot of the complex physics actually going on over here. But obviously important, very, very important thing is that this molten polyethylene is grows actually with time. By the time passes, this is actually growing. Then eventually, this is the backlight image. You have polyethylene burning over here. You have flame, but since you have the backlight, you don't see the flame actually. But flame is over here. Right? Polyethylene, the molten layer is getting large, then eventually couldn't suspend it, then falling down. So this is actually not much expected for me, because once this is done, propagation of the wire and the flame over the wire, it's never say that steady state problem. If this is a steady state, molten layer size has to be the same as always, but it actually get increasing and dripping off. So this can get, you get the cycles. So you get the many dripping off under some certain conditions. This is the conditions and the variety of conditions, and this is the time versus the volume of the polyethylene we can calculate from these images. And this is almost constant, but this is increasing. Then discontinuity of happens over here and increase. What happened over here is the molten layer is dripping off. This is increasing, and dripping off. This is increasing, dripping off, increasing, dripping off, increasing, dripping off. So most of the low pressure case, dripping off is promoted. And this is interesting results. If we have the faster frame spreading case, dripping off is substantially you can observe. So this is the kind of a pronounced. Growth of molten polyethylene in low pressure, or we should say the lower Grashof number is more pronounced. That's why at first time I mentioned that there is some kind of zigzag motion of the frame front at buzzers of the time. That is actually the time that the molten layer is dripping off. Then you have some bumps like this. But fortunately or unfortunately, average frame spreading rate is almost a constant. So we should say the frame spreading phenomena over the wire is not a steady state processes, but also you should say that quasi steady state processes. So what have been observed through the experiment? We actually have three important facts. The one is heat transfer through the conductor material is very important to determine the frame spreading rate, so as to the flame. The second one is frame spreading process is probably you should state quasi-steady, not the steady state. I think this is the first. I think my group is the first group to saying that the wire spreading is not the steady state. The molten layer polyethylene fall off quite frequently, so this has to be counting on if you try to get the more secure fire design of the material of the cables or something like that. This has to be considered about that. So to think these three items are very important experimental observations. So we try to model how to explain or frame spreading rate, or what is the process of a frame spreading case. These three has to be considered. But mainly, first one, I took that is very important for the modeling purpose. Since the heat transfer through the conductor is one of the very, very, very important issues to be considered for the modeling. So I just try to simplify very, very simplest case, which is 1D heat transfer problem through the wire, through the conductor. So the frame is moving over here, moving like this. So if you stay the frame over here, you're putting the wire the same speed as frame spreading rate. Then you have stay the frame over here, all right? Frame spreading over here, but if you taking the wire the same rate, your frame is fitted over here. So this is the case. You're sucking up the wire as the rate of the frame spreading rate, and your heat will be heating up from the frame or either wires. Then through the wire, you have heat flux over here, and there's some portion of the heat flux is used for melting the polyethylene, like this. Then the rest of that is transferred this way. So one heat transfer mode, like this way, is very easy to be simplified, to be formulated anyway. So this is the advection term, this is the conduction term, this is the heat loss term to the polyethylene. You can non-dimensionalized, this is described by the star, this is non-dimensionalized equations, one-dimensional heat transfer equations. So nothing is difficult. Then you will see that two of non-dimensional numbers, actually, non-dimensional numbers in the coefficient over here. Here you have convection term dividing by the diffusion term. So this is the same as the Peclet numbers. So you put the Peclet number over here. Here, this one, there's no universal numbers. So I just say that this is the large lambda. The Peclet number is denoted like this. The lambda is defined like that. So what means that this Peclet number and lambda is two non-dimensional numbers actually controlling this system, temperature profile. So what is this Peclet numbers and lambda has correlated? This is one of the interesting stories. They're taking that there is two non-dimensional length scale, L and R. L is a length scale for actual direction, and R is radial reductions. So taking L is flame thickness, the flame width, and O is the wire diameters, then you can plot for every single wire combustion case in the phase plane of Peclet number on the lambda. Then every plot is following on a single line. I tried this one almost 100th time to correlate somehow, but this is the best shot I got. And this is pretty good. The why Peclet number and lambda has to be the linear correlation, that's one of the good things to be thinking about. So we know that how to describe the Peclet number, how to describe for the lambdas. So we can just dividing lambda over Peclet numbers to get this tangential, this tangent. This is the results, and here you have K is like this. So K is almost like over here. It's determined once your cables is fixed. If you pick the cables, this number of the K is already there. RC is the core, the radius of the core. The AC is the thermal conductivity of the core, and such and such. So you know the numbers once you specify the cables. So this is the cable dominant constant, cable specified constant. Now here L over BSP is less. And these two, lambda over Peclet number has to be constant for all the cables tested over here. So which means that L over BSP has to be also the constant. All right. K, again, the K is determined each cables. So each cable has a different K numbers. But associated with different K numbers, if you have the different L over BSP, the resulting the constant for all the cables. So what is means of the L over VSP is that this has the same unit of the time. So you can say that this is a tau. What means that L is flame length or flame width, and VSP is flame movement. So T is actually the time, how long time you are staying over here. So that's the kind of the residence time. So this is the residence time of the flame, and this is the cable specified conditions. Now that has to be constant. So anyhow, these results mentioning that why these two non-dimensional parameters appeared, just because we assuming only one-dimensional heat transfer mode. But only one-dimensional heat transfer mode we considered by taking the L is flame width, and we find this kind of good correlation. So which means that heat transfer inside the cable actually dominant for to determine the flame spreading rate. There's some trick is there why we choosing the flame width as the length scale of the actual condition, the actual direction. This is because if you're taking L, which means that you have some contribution from the flame. So this is the kind of representative of the contribution from the flame. And the formulation is contribution from the solid, from the wire. So these two combined give you a good universal correlation like this. So this is these are the things I got actually in the controlling cables, in the wide range of the controlling cables. I don't think I have not much time left, right?
5 minutes.
Yeah. So what I'm trying to doing that, try to upscale, right? Since we are just using the controlling cables so far, even though the variety of the cables we created by order made, but many people say that okay, you just play with the artificial cables, so that's not the usual. That's not actual cables. So what happens to the actual cable is, so I'm trying to switch to the actual cables file and cables combustion. So sample is so-called eco-material cables. This is the Japanese-made low toxicity cables, low smoke, halogen-free. I don't know this is really right or not, but they're commercializing low smoke and halogen-free. This is really safe, but actually not so safe. Then we try to burn these cables as a test. This is the cross-sectional view of the eco-material cables. We're actually using two different cables, 4-core or 10-core cables. Then this is a scaling up. Right? This is the wire we actually used. We made it by ourselves. And this is a 10-core cable, and this is a 4-core cables. And this is just only one core. If you're separating for 4-core cables, you can sucking up just one core cable like this. So try to burning this thing to this thing, this thing, this thing. As the same apparatus we we did, like this. This is the 1C cables. Again, the same things. One end we got the igniters. The one flame generated, flame is spreading over here. This is the 1C cables, only one core. So larger flame is made, but almost a steadily flame is going to be spreading. During this spread, again, the molten layer is dripping off very frequently. So this portion gets very dirty. This is a result of the 4-core cables. Even though the cable is slightly bending, but this is actually not good results. But mostly the flame lengths, once made the complete frame constant frame length is moving like this. The same thing for 10-core cables. It's also very bending and very hard to stick with over here. Very larger frame is actually made, and very wider frame you can get. But once you make the flame, somewhere you burned out, so you have some certain length scale of the flame is moving eventually. This is the burnt results. Once you burnt the cables, of course, core was remained, and the PE molten polyethylene was really gets dirty over here. This is taking a picture for control of the cables. The scale is not actually the same. The scale is the same actually. This is the control cables. This is the 1C cable, 4C, 10C. So too much differences. However, as mentioned again, the flame length, flame width is almost constant for 4-core cable or the 10-core cables. So we're just taking this number for some specific length scale for 4-core cable or 10-core cables. Now, what about the frame motion, frame front versus time? 4-core cables is very scattered, but you have some rate of frame spreading. So if you're taking over here, you get the average frame spreading rate. You can determine, even though for 4-core cable or 10-core cables. Again, the frame shape is too much difference, but you have certain lengths of the flame is generated, and you have constant or average frame velocity, you have it. That's the same thing. So if you have the flame length, the frame width, and you have the frame spreading rate, you can plot the results of a 4-core cable or 10-core cable into the Peclet number lambda correlation phase chain, phase plane. This is the results. Okay, this is the results I already shown that almost one over here, and just magnified over here. Then this is the controlled cables, all right? And 10-core cable, 4-core cable is existing over here. So small scale stuff actually can predict the large scale stuff. So which means that even though these scale up results is very large, it seems like not the large scale, but the middle scale, and pretty much difference. You fluctuate a lot. But you have the average value can be well distinguished or well predicted by using the small scale test. So this is the good results. It surprisingly works. I thought this doesn't work, but it actually works. So I was very surprised, and my student did a very good work to get these results. Let me summarize my talk. Cable fire in space could be simulated with low pressure conditions by using the graph of number similarities. Heat transfer along the wire is a dominant process to determine the frame spreading of the cables. Peclet number lambda correlation at this moment works pretty well for single cable spreading case. So which means that even though the control cable case, but also the real wire case, real cable case, heat transfer along the wire is always a dominant mode. The falling off the molten polyethylene is underrated fire source. This is really gets dirty, and melted polyethylene was almost forming the pool underneath of the test section. So once you lighting up, sometimes later it's burning up. So since this is the polymer combustion, melting polymer is present somewhere else, that can be causing another fire chance. So cable fire is not only the cable burning, but also the molten layer dripping off that can causing the fire. That's also one of the cable fire you can think of. So this is the concluding my talk. Importantly, I have to say thanks to my financial supports. I got many grants and sufficient money to doing this kind of experiment. And my co-worker is Dr. Wakatsuki, and many students and many professors. Thank you for your kind attention. This is my talk at the end. Thanks.
Questions?
Yeah.
How long were the samples you were using inside the pressure chamber? They would say
It's about
20
26 meters.
20 centimeters.
If you're long enough, that's much better. But if you're long enough, just only 2 supports is not good to make it straight. So essentially, we had a tension, some structure to pulling the cables. But if we have the very high tension during the frame spread, since the wire is expanding, so it's, the wire getting thinner if you had a higher tension. So you need to control the tensions anyway. So that's the kind of things we are actually doing. So by using copper wire, it's very easy to be expanding. So that's very difficult to do so.
What is the reason for cable fires? Is it external source, or is the metal inside the wire that is heated first?
Since my objective, the first motivation is for space fire research. And the space fire research, mostly what is the most causing the fire is the electric cause, the electric fault or some short or something like that. But the wire starting fire is one of the potential cause of the fire in space. And recently, since I got my grant from nuclear power plant companies, or power plant safety organization or something like that, nuclear power plant also working for the cable fires, how the cable actually behaves during the fires, because there's a lot of the cables in nuclear power plant. Once you get fires, something over there, then destroy everything. So if you can't control, if you try to stop, but if the cable is down, you can't control. So that's really a severe problem for them to understand how the cable try to burn and how cable doesn't work. So that's one of the reasons why cable fire has to be considered. And also, aircraft case, you starting from the short or something like that from electric circuit, that's also one of the potential causes. And actually, it actually does. So even though that is the quite rare case, you can say that that's a rare case. If you have the fire, this is the case of the fire, only couple case for the electric fire. But once that happens, it's always death. So you need to caring about. That's one of the motivation. We're there, which is 30 kilopascal is that in a case. If you're reducing the pressure, you have the diffusion transport is enhanced. So you're diffusing a lot of the heat to the outside, but you have also diffusion coming into it. The fuel and the oxygen is also easy to coming into it. So the temperature has to be the same. Temperature has to be balanced, but the heat flux is of course different as compared to the normal flux case, normal pressure case.
Said that the reason why the Q1 you divided the Q1, Q2, Q3. Yeah. The reason can you see? Yeah, you said that the reason Q the 50 kilopascals Q1 is higher than the 100 kilopascal. You said that the reason is the shape of the flame. It is. Do you think it is made by the conduction? I think the flame shape is so cute, 50. It means but 100 kilopascal in the flame, the flames more higher, and I think there is a more convection and there more buoyancy and more convection, and I think it makes the less convection and the shape's color looks very blue. It means there is no more radiation than 100 kilopascal. I think other heat loss is just conduction. So do you think it is the low pressures?
The radiation is, of course, very, very small. But in this case, I don't think the radiation is most dominant case for heat transfer. Mostly, the dominant case is thermal conduction. So this is why the reason that the shape always does to get a higher heat flux, higher heat conduction rate, or higher heat conduction, higher amount of the heat. Of course, as you mentioned, compare with the radiation heat flux over here, of course, this one is much more. But the amount of the radiation heat flux has to be quite small as compared to the conductive heat flux. But I understand you saying that the 100 kilopascal you had more buoyancy flow, so your frame shape is like this and not like spherical shape. You have this flow, your frame is pushing, so your frame width is going to be shrink. You have buoyancy flow. Since you have buoyancy flow, your frame is something like a shrink, pushing back to the buoyancy flow. So somehow that's the reason you have narrower flame width. Actually, you can see in that. If you go down to the low pressure case, you also have the same buoyancy flow. Your diffusion transport is more enhanced because you are less molecules there, so it's very easy to be diffused for each molecules. So that's why around the frame, diffusion transport is much more stronger than the buoyancy incoming flow. So you have expand. So the frame shape is different, and I think this is the more very easy to understand to how the frame spreading is getting higher. But I may be wrong.